I'd like to start the second lecture with a recap, abridged recap of what I left you with last time, that is yesterday. So you see, so first we discussed this concept of coupling an external background gauge field, which geometrizes, which as a bundle to a charged current of a point-like particle, right? Described by the motion of a charged point-like particle. And so we had, first of all, we were sitting in this. Maybe I will change. Sorry. Yep. So I told you that it is useful to start by considering those Aharonov-Bohm pairs of cobordant trajectories of a point-like charge in order to lay your hands on the differential geometric structure that you need in order to even couple the gauge field to the trajectory, to the current. Then ultimately we'll cut the Aharonov-Bohm pair into two trajectories and look on one of them. But then the structure that we put on the circle, or rather the loop in the space in which the charge propagates, in the first place, will tell us how to close the transport operator, which the line holonomy turns into once you cut it off. Because then it's no longer a good thing, it is not invariant under the arbitrary choices made, and you have to somehow close this transport. But that will come after. So we had the following situation. We had S1 as our space time of our 0 plus 1 dimensional field theory. It was mapping by this field X into a manifold X, on which I had a metric G. There was a two form with, as discussed, necessarily integral periods. So when evaluated on a basically on a loop, it should give something from 2 pi z, so periods of f. I'm setting q equal to 1 in 2 pi z. And then this f geometrized as a higher geometry, as a surjective submersion over x, which I shall refer to, in order not to confuse you, by the name of the electromagnetic bundle, because as it happens, it's also a principal U1 bundle, a principal circle bundle. So this will be our electromagnetic bundle. It comes with a connection 1 form. So it's a 1 form on L with values in the Lie algebra of the group, which is U1. So the Lie algebra is R. So with values in, I will somewhat artificially write it like so that it combines with what you learned elsewhere in the other context. And so we have this stuff. And then the topological term in the action functional, or rather in the Dirac-Feynman amplitude, is given by this holonomy of L along the X image of S1, which is one cycle in X. Okay? And now the holonomy had various properties. Subsequently, we abstracted this notion of a principal, let me write it, principal U1 bundle. So we abstracted this notion and discussed principal G bundles for arbitrary groups. So we would have some manifold M or some base, maybe let me call it. We were having some base, and over it a surjective submersion with a typical fiber given by a liquid G. This guy would come with a 1 form with values in the Lie algebra of G. And this we were using, instrumentalizing, to gauge symmetries. Well, that we haven't done yet. Oh, we have done it for, in the case that the field theory in which we note some kind of global symmetry is defined in terms of G invariant tensors, then just the minimal coupling, replacing derivatives by covariant derivatives, and representing sections in the associated bundle locally as locally smooth profiles over the spacetime into F, to the space of internal degrees of freedom. we were using these principal bundles, which I shall refer to this time as gauging bundles, to render local a global symmetry of the field. And now I want to combine the two pictures. So I started considering an isometry of this metric space, which is supposed to be, and for that I got conditions, which is supposed to be an invariance of the derived Feynman amplitude for x, which, just to make it clear, the derived Feynman amplitude for x was exponent of I, and then the metric term, depending on how you want to play it, you may take it in the you may take the energy functional or the length functional. Doesn't matter too much. Well, it does matter because reparameterization invariance, but it won't matter here. So let me make it simple and take this time around the energy functional, which describes geodesic flow of the charged particle, but then I couple it to L. Okay, this is. So now I want to discuss global symmetries of this theory, which happens to be defined in terms of an electromagnetic bundle in the first place. So I look at isometries of this metric background xg. X plays the role of the space of internal degrees of freedom of this theory. And I derived, or said what they are, conditions for the infinitesimal symmetries to be symmetries. Yeah? So for the vector fields, whose flows generate the symmetry group G to preserve this Dirac Feynman amplitude. Just to remind you, the vector fields for the symmetries G were supposed to contract with F in this Hamiltonian way. Okay. Good. Okay. So good. So now I said the following. Suppose that the electromagnetic bundle L is trivial. So it has a trivial connection 1 form and an invariant, G invariant. Then I know how to correct this expression just by minimal coupling. And then I reinterpret the minimal coupling, which would look like so. I would have this A, which is now a 1 form on X, not on L, with values in R. I would couple it not to Tx, which is the pullback of A to S1, but I would couple it to the covariant derivative of a section of the associated bundle, which I also assume the gauging bundle to be trivial for simplicity to draw conclusions. So I assume both P and L to be trivial. L comes with a global connection 1 form on the base. So does P, except that the base is in this case, the base is, in our field theory, it's S1 now. Okay. And so A is a 1 form on S1. Let me maybe call it whatever, A, maybe this A. A with values in the Lie algebra of the group. And now I'm replacing this pullback of the connection 1 form for the electromagnetic bundle with the covariant derivative. Okay? And the covariant derivative is defined in terms of the connection 1 form on the gauging bundle. And as I expand it, I get the, so to speak, morally speaking, I get what I had before. Well, T phi. Plus I get a correction linear in A, capital A. And I interpret the resulting Dirac Feynman amplitude as the old good holonomy for the electromagnetic bundle with a trivial correction coming from A. And let's look at, this was the start, the end point of our discussion last time. Was it? Yeah. So you see, I interpret my result as follows. Not this one. Yeah. So instead of the electromagnetic bundle which I started with, I now move to the target space extended by the total space of the gauging bundle, which in my argument, useful argument and silly argument, was trivial, but now I make a bold step forward and say, okay, what I'm getting is the following. I have a bundle over P times X. On X, it's my old good electromagnetic bundle, and on P times X, I have this correction linear in the connection on the gauging bundle, which came from minimal coupling. And it's just this. It's co-momentum contracted with A. Co-momentum contracted with A. And then I have to ask myself, under what circumstances this beast descends to the quotient of P times X, on which the group acts freely and properly, that is to the associated bundle, which is the field bundle for the field theory with G gauged, as discussed earlier. Okay. So I'd like to derive that by playing a little bit with a field in the theory with symmetry G gauged, which, if you recall, these were sections of the associated bundle, and so using local sections of the principal bundle, the gauging bundle, I could visualize them, I could represent them as a family over the trivializing cover of the gauging bundle, a family of locally smooth contours in F. Glued by what? Glued by the transition mappings of the gauging bundle. But then now, what do we have? We have a field theory, 0 plus 1 dimensional field theory, in which fields are locally smooth and their discontinuities are captured by the action of the gauging group, mediated by the transition mappings, valued in that group, transition mappings of the corresponding gauging bundle P. So, so I have those local fields. I recall here how they were defined. So you remember that the global section of the associated bundle was the same as an equivariant map from the total space of the gauging bundle into the typical fiber of the associated bundle. And so when pulled back by a local section of the principal bundle, it was giving me a local contour in F, locally smooth contour in F. And so I have this fantastic picture in which you see my field theory has this standard smooth form on patches of space-time. Those patches are mapped into F, but as I cross from patch to patch, the smooth maps change. They change by the action of the transition mappings of the gauging bundle that live somehow on the codimension 1 submanifolds in space, at which the jump, the discontinuity occurs. And so I have to ask myself the question, how do I make sense of the field theory in the presence of defects? By now, it's completely natural. You gauge the symmetry, you end up with defects. You may pretend like there are no defects because you have global sections of the associated bundle, but try to couple those sections of the associated bundle to the data of the theory prior to the gauging. Right? What is it? I mean, it is something. I will show you what it is, but on the first naive guess, I have no idea what to do with a section of an associated bundle. Here I do. Locally, I have I have this minimal coupling of the electromagnetic bundle to the connection on the gauging bundle, or rather its trivialization. And now I just have to take care of the defects. The problem here, I would have the same problem in a tensorial. But there, due to G invariance of the tensors, it wouldn't matter where I put the defect. Because the difference in the value of the action functional as I shift the defect, so change the local presentation of the matter field, would be a gauge transformation. The gluing by transition mappings is a gauge transformation. And I know that the theory, due to G invariance of the tensors defining the couplings, is G invariant. It is a gauge invariant. So it doesn't matter where I put the defect. So nothing depends on the arbitrary choices. But now I have the holonomies. And another problem here, because I've cut the holonomies and they were only well defined on cycles. In the case in hand, on one cycle, loops. And now I have segmented the loop into edges which sit squarely in trivializing neighborhoods, trivializing for the gauging bundle being over S1. Makes sense of cut open holonomies. I have to glue holonomies, rather transport. And I proposed this question together with Ingo Hunkel at some point, and realized that what you have to now do is you keep the former description in terms of the electromagnetic bundle, which you pull to segments, but the vertices of the segmentation, in the most general setting, if you have a defect, I'm not saying this one I will describe in detail, but if you just have a discontinuity of a field over a point in S1, then you're supposed to map this point to another manifold with that structure. So what should be this structure? You see, as you're approaching the discontinuity, the two field configurations on either side of the defect, they approach their limiting values. And so I have a pair of points in this case, a pair of points, or rather pair of configurations of my field theory at the defect. So when I map the defect junction, the vertex of the segmentation, where the defect, the discontinuity appears, into this new manifold, the new manifold should come with two maps to the manifold in which I embed the segment, so as to reproduce the two limiting field configurations. That's not all. As it happens, and you derive this, you don't guess it, you derive this, what you should pull back by this map of the defect junction into this new manifold is a special isomorphism of electromagnetic bundles with connection. In other words, you see, previously I used bundles to describe holonomies. Now I need bundles to describe segmental holonomies, and I need isomorphisms of bundles to describe junctions. So a field theory with defects in the presence of charges, defined in terms of these differential characters like holonomies, calls for the full category that I can associate with the geometrization. So at the bundle, I have bundle morphisms. Later on, I will have jerks for patches in a two-dimensional space-time. I will have one-dimensional defects between them, so I will need isomorphisms between jerks on those correspondence spaces into which defect lines will map. And then there will be the lines, defect lines may intersect. And then I will need morphisms between morphisms to be pulled. Yeah, it'll be a two-category. Your first two-category, maybe for some of you, maybe the last even, which I will pull to defect junctions. So you really need this fully fledged structure of a higher category that you associate with the geometrization of the de Rham cocycle, the integral of the de Rham cocycle, which describes your Maxwell-type field, which couples with the current. Okay, let's go in here. So so I told you that it's not any isomorphism of electromagnetic bundles, but as I pull back the electromagnetic bundle to the correspondence space into which the defect maps, by the two maps into X, iota 1 and iota 2, that give two limiting field configurations at the defect, the two pullbacks should be isomorphic, but not on the nodes. What I can allow is a correction by a trivial principal U1 bundle, which means I should correct the connection one form by one form on the base, so on Q. Okay? And now I can describe precisely and concretely the particular defect that implements the gauge symmetry, because I know what the jump is, and so how to model the correspondence space Q, because the jump is just the action of the group, and so by transition mappings of the gauging principal bundle, and so I have the following. I told you that in order to perform minimal coupling, which is good in over those segments into which I now cut my one-dimensional space-time solid one, since I want to have those corrected electromagnetic bundles with a trivial correction coming from minimal coupling, I prefer to think of the target space for the segments as OI times X, where OI is the trivializing open trivializing for the gauging bundle P. And then over the segments, I just have those bundles L, A, I as found previously. And I stick to my guns there. Now I just described the junction. But the junction can be easily modeled as OIJ, which is where the gluing happens, the intersection of the two trivializing opens, OI and OJ, times X. There I sit with one of the fields, say the one to the left of the defect. And then what the two maps are projection to that map, to the left of the defect, and action with Gij evaluated at the junction point. These are the two maps. And then my formal result is telling me what I should pull back, what isomorphism, electromagnetic bundle, extended electromagnetic, minimally coupled electromagnetic bundle isomorphism, I should pull back to the junction, namely this one, where lambda is the action, I'm acting with the transition mappings of the gauging bundle, and projection 2 is the projection. But now the question is, I told you that there is this, I have this 1 degree of freedom, which is like correcting the bundle on the right by a one form, a global one form on the correspondence space. Am I at ease to choose it? Should I choose it somehow, or is it fixed? In order to answer this question, I have to remind you that if I insist on there being an isomorphism of principal bundles with connection, the curvatures should match. And I know the curvature of this guy, I know the curvature of this guy, and this is the sought after one form. So I just perform the calculation and find out that this one form is actually fixed. I may have this isomorphism, but only for a fixed one form. And this one form is actually defined in terms of, it's our old good omega. It's defined in terms of comomentum, which I introduced previously. Previously it was comomentum contracted with precomposed with the connection one form. Here it's the comomentum precomposed with, if you will, a connection on the principal bundle over a point, which is just the Maurer-Cartan form, left invariant Maurer-Cartan form on the group, if you think of it as a principal bundle over a point. Okay? And so, what I infer, since the curvatures match, going in one direction is easy. If I have an isomorphism, I certainly have equality of curvatures. But if I have, as I have just checked, equality of curvatures, it does not mean that I have an isomorphism. What I do have is an isomorphism up to a flat bundle. Curvatures add when I tensor bundle. So I have this isomorphism up to this delta. So already I can see that delta apparently is quantifies for me the obstruction to having a well-defined theory with gauge symmetry defects. Because if I have it, I don't have this form here, and I'm screwed. And I will tell you exactly how screwed I am, I mean the computation that is, because the rest you probably guessed, by looking at how this connection-corrected electromagnetic bundle, so minimally coupled electromagnetic bundle, changes under a gauge transformation if I assume the following, which follows from the invariant property of from the transformation properties of the curvature of L. So the maximum field, in other words. Okay? So then I realize that if I pull back my extended electromagnetic bundle by a gauge transformation, and I simultaneously, just recall how covariant derivatives were gauge transformed. You were supposed to gauge transform the field and simultaneously gauge transform the gauge field in the connection, so that the whole thing transforms covariant. Okay, here likewise, I have to transform the bundle L, and I have to gauge transform the connection one form, which sits in the extension. Here, like here. It sits here. 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 Okay. So when I do that, I realize, and this is simple. I mean, I know how how L transforms. So all it takes to compute this is to transform the trivial correction, but the trivial correction is tensorial, so I'm just pulling back the tensor along a gauge transformation. I can do that. You can do that too. So then I realized that due to this potential appearance of a flat bundle, which corrects this isomorphism, I get gauge invariance of the minimally extended electromagnetic bundle up to a contribution from the flat bundle. So now I see more concretely how this flat bundle constitutes an obstruction to having a gauge symmetry. Because, you see, if I now compute the holonomy of the minimally extended electromagnetic bundle, and I perform the gauge transformation of the holonomy, I know that the metric term is gauge invariant by itself. Because I coupled it and the metric is a G invariant tensor. But if I now perform a gauge transformation of the holonomy, I will get, so the holonomy of a tensor product of two bundles is the product of the two holonomies. Okay? So I get invariance of the holonomy bit up to a holonomy contribution coming from the flat bundle. And it's a theorem which says that holonomies vanish on all one cycles if and only if the bundle for which you compute them is trivial. Is trivial. So not just flat, but trivial. But trivial and flat, meaning I can just forget it. There is no bundle. And now I see in what sense this bundle delta is an obstruction to gauging, something which we call a gauge anomaly. An inability to render compatible the symmetries of the action functional that were before the gauging, before rendering some global symmetry local, and after. I cannot gauge this theory. There is an anomaly. We had a small gauge anomaly, which was the obstruction to having this Lie algebraic structure on the functional span of the symmetry sections of the generalized tangent bundle of type 1,0. That was the small gauge anomaly to gauging the small gauge, to having small gauge transformation, so homotopic to the identity gauge transformation. Okay? And here we have a gauge anomaly for the large gauge transformation. And it's quantum mechanical, intrinsically quantum mechanical, because so are the holonomies. The transport operators, if you cut them in the pre-quantum bundle, that I will discuss later. Anyway, so now, okay, so this means basically, what does it say? This means that I should have this, principal bundle isomorphism on the nose. But is that all? In order to answer the question, if that is all, I should entertain the following Gedanken experiment. So you see, I now have the following picture. I have my S1. Over it, so I have segmented it into pieces which sit in trivialization domains for the gauging bundle P. I now, over those segments, I send smoothly into X. And with this smooth map, or rather with the smooth map identity X, which maps me into OI times X, I pull back the extended electromagnetic bundles. I have to the defect sitting between the segments, I pull back the data of a very particular isomorphism, which implements the gauge symmetry isomorphism. I looked at it previously. I looked at it at the previous slide. I mean, it's defined by this upsilon, which was the isomorphism here, this one, which I now assume, because if I don't have it, if I have a flat bundle correction, I have an obstruction to gauge invariance. So I'm assuming this, and out of that, I can define a suitable bundle isomorphism on the correspondence space Qij. As it happens, it's this guy. It's this guy. But then you see, it's completely arbitrary where I choose to have the defect which separates the two segments. I mean, why should I choose it here, not there? Anywhere in OIJ, I have Gij, I can act with Gij, and I can glue the two locally smooth profiles. So nothing should depend on where I choose the defect to lie, as long as it is within Gij. So the question is, how does the action function or Dirac amplitude changes if I move the junction? You can compute it quite expressly, because what you have is now, here you have the pullback of the extended bundle with data AI. Here you have the pullback of the extended bundle with the data AJ, local trivialization. And here on the defect, there's the data of this isomorphism phi Gij. So you just define it, you put the vertex at one place, at another place, you compute you take the quotient of the two Dirac-Feynman amplitudes and see what happens. Nothing happens. Which means that you are, so sanity check done. You may actually move the defect within OIJ. But this is not an innocuous, it's quite a consequential observation. By the way, defects like that are called topological, which means we can move them freely at no cost in the action function. Because when you come to think of it, what it means to have a topological defect means that the Hamiltonian is preserved by that is continuous along the defect. Why? Because the Hamiltonian is the generator of translations along this line. So as we translate defect at no cost in the action function, it means the Hamiltonian is preserved, which is a good notion of symmetry. Not just mapping the states to the right and to the left, but mapping the energy structure. Okay, good. But now what does it mean that I can move the defect? I may have the following configuration. I have one trivialization overlapping with another trivialization, overlapping with a third trivialization. And now let me imagine that I have originally put the defects thus. There's a defect between the I trivialization and the K trivialization. Then I jump from the Kth trivialization to the Jth trivialization here. And then from, no, sorry, I did it the other way around. So from I to K, from I to J, and then from J to K. Well, I have three defects, and I'm jumping like bah, okay? But since I now have a topological defect, I can push the two defects, the extreme defects, to where the middle one lies. And now I have another arbitrary choice. Should I go tap, tap, or should I go tap? Oh, let me differentiate. Should I go tap, tap, or tick? Right? So the difference between tap, tap, and tick can be described in a more quantifiable manner. And then it turns out you just compare the composition of the two bundle isomorphisms. Tap, one bundle isomorphism. Tong, the other one, with tick. This is a comparison between the composition of the two bundle isomorphisms. This is how bundle isomorphisms get composed. And the other one. And what you draw from that is a condition on upsilon on G times X. And damn it, that's the equivariant structure. The existence of upsilon and the coherence condition that I've just derived from the tic-tac-tac from the topologicality of it. Now, ain't that lovely? Right? So, good. So, I wanted to tell you a little bit about simplicial structures, but there are so many things that I won't be able to tell you about. The punchline is that in order to have a meaningful theory of gauge symmetry defects, which implement the gauging, and how so I will tell you later on in a moment, I need an electromagnetic bundle over X into which the segments map. I need a very particular electromagnetic bundle isomorphism, preserving connections over G times X. Why G times X? Because I have Gij acting, and this sits in G. Okay? And then I have a coherence condition over G times X. Why G times G? Because if I push the two defects together, I have Gi and Gjk, Gij, Gjk, and Gik is already defined by the other two because we have a cosine. Good. So, and now that we have understood that we need the equivariant structures, we can play smoothly and pretend like we've never done this dirty job and just do the following. We pass to P times X. Remember, sections in the associated bundle, which is the G quotient of P times X, were our fields. I want to see them now. So on P times X, I have the pullback of the electromagnetic bundle. I extend it minimally, but now couple the co-momentum with the connection 1 for an on P. Not its trivialization, but the connection 1 from on P, the big object, on the total space of P. All right? And then I realize that if I, as discussed a moment ago, if I have a G equivariant structure on L, then this corrected bundle has not any G equivariant structure, because this one, see, had a very particular non-zero correction to this isomorphism, a very particular one. But this one has such an equivariant structure with the correction equal to 0. And now we go back to the theorem, which says if you have a principal U1 bundle over the manifold on which the group acts freely and properly, as it does on P times X, and this bundle has an equivariant structure with the correction 0, then it's a pullback of a unique bundle on the quotient manifold. Aha! But that means that I now, so that's what I'm saying. But this means that I have a unique bundle associated to my minimally extended electromagnetic bundle on P times X. I have a unique bundle on the associated bundle of the gauged model for the point-like particle on P x lambda x. I just take that bundle, uniquely determined by the minimally extended electromagnetic bundle, and pull it back by what? By the matter field, by the global section of the associated bundle, and I'm done. And so here's the result. As you can see, it's an understatement to say that minimal coupling doesn't quite work. You have to do some extra work in the presence of non-tensorial. For tensorial couplings, moreover, defined in terms of G-invariant tensors, so many assumptions, you have minimal coupling. If you don't have a tensor, and even if it's not G-invariant, you cannot be just minimal. That's case study. Okay? Okay, but now we're up for third geometrization. So the question is, in what sense are we actually describing, as advocated at the beginning, this reduction of the space of internal degrees of freedom from F, generic field theory, to F mod G. And in our case, from X to X mod G. Mind you, first of all, X mod G needn't exist as a manifold. We're just modeling by those locally smooth sections. And why does it make sense to model it by locally smooth sections? Because you see, if you're modeling something on the orbit space, you're perfectly justified to take discontinuous maps, which would collapse to continuous maps on the orbit space. A long time ago, when you were not born, people like Rafal, Witten, and Jost, was it? I forget now. Definitely Rafal and Witten wrote a fairy tale about strings and orbifolds, and introduced what is known as the twisted sector of string theory. That's your twisted sector. Where does it come from? Non-trivial gauging bundle. Because you see, if I take a trivial gauging bundle P, I can always choose the local section such that the gluing is by identity. And I have a smooth contour. And the only thing that the gauging has, the effect the gauging has, is identifying field contours, which are related by a F1 index, smoothly so, group action. But these are all smooth contours. What is non-trivial is the non-smooth contours, non-continuous contours. And the bundles, namely non-trivial bundles, for which I cannot choose the transition mappings, Gij, everywhere equal to identity. These are the non-trivial. And if X is non-simply connected, I will, F1 is non-simply connected, so I have them. The question is, should I consider them? Maybe I'm done if I just consider the trivial principal. And if some of them, then which ones? I mean, I had this inkling that since I'm going to have this twisted sector, I mean, this field configuration upstairs, I'm modeling because X mod G may not be a manifold, will be perfectly all right on X mod G. But which ones should I take? And the answer is all of them. And the deep argument touches on Yoneda lemma and the universal construction for principal gauging bundles, which I will now sketch or wave my hands about. So you see, let's go back to the far past, the far east, whatever. No, it was in France. Cartan-Borel. Let's discuss Cartan-Borel. Oh dear. Oh dear, oh dear, oh dear. Let's yodel it. Kill the time. Ah. Lovely. Yeah, we have it. Good. So you see, I told you that you should erect a principal gauging bundle, G bundle, over S1, or the space-time of your field theory, in order to gauge the symmetry. But there is a notion of a universal, which for our purposes is a purely formal object because it's an infinite dimensional topological manifold. So it's not directly amenable to manipulations, at least not by us, but still it is very useful in the following sense. Whenever you construct a principal G bundle over some manifold, a kitten dies somewhere. But on top of that, there is a unique up to homotopy map into a space called the classifying space, for which there is no model, over which there is a unique principal G bundle, the universal principal G bundle, for the following reason. Your bundle that you have constructed is the pullback of that bundle from the classified space. So there is one bundle to rule them all, up to homotopy, by up to homotopy unique maps, mapping X to BG. All right? And now you can play along. And if you have a universal principal bundle, you can construct a universal associated bundle. And Cartan and Borel tell us that, so this universal associated bundle, of course, as before, it fibers with the typical fiber F over the base of the universal principal bundle, so the classifying space. But whenever, so the typical fiber, fibers principally over the orbit space, then by symmetry, the universal associated bundle is a bundle over the orbit space with the typical fiber EG. And now comes the miracle, EG is contractible, which means that the topology of the universal associated bundle is the same as that of the quotient, which is why we call it the homotopy model of the orbit space. So its cohomology would be the same as the cohomology of the quotient, and if the quotient doesn't exist, we just take the cohomology of this guy to be the definition of the cohomology of the orbit space. And why I speak of cohomology? Because, ladies and gentlemen, the Maxwell field is cohomology. Its geometrization is cohomology. Right? We did that. So, and now, here comes the punch. So, your concrete, specific, associated bundle is now pulled back by the same classifying map of the universal associated bundle. So now if I have a section from X into that associated bundle, if I compose it with phi, by which I pulled back the universal associated bundle, and then the mapping to the orbit space, I get a mapping into the orbit space. But now here's the catch. This guy is a perfect model, homotopy model of the orbit space, but this one isn't. It's just what category theorists would call the X point in this homotopy model. You know, so there's this Yoneda lemma theory which says if you have an arbitrary, more or less arbitrary, let's say small category, in which you have objects, you can inscribe the full, and faithfully so, the full information about the object which the category carries. The category gives you some resolution as to your knowledge about an object. And you can inscribe the full information that the category carries about the object in all structured maps into that object from all other objects from the same category. It's called the Yoneda embedding. And now what you see here is that I have this associated bundle over X, which by the inducing map phi maps into the universal guy. The universal guy carries the full information about the orbit space, but I'm only probing it with this map phi. In order to get as close to the full information about the orbit space that the universal associated bundle encodes, I should map into it in all ways possible. It will be just the mapping of my associated bundle, of X, if you will, but always possible. So in other words, in order to really get descent to F mod G, I need to consider all isomorphism classes, because the statement goes that if I have two isomorphic principal bundles, there is a homotopy between the pooling maps. So I only need to consider isomorphism classes of bundles, but all of them. And now we understand why. All twisted sectors have to contribute. Okay, good. Swell. Where are we? Yeah. Good. Right. But now let me describe in more practical terms how this descent to F mod G, because you may still not be convinced. I mean, well, there is this homotopy model. I'm sort of mapping by homotopy, by a representative of the homotopy class of pooling maps, blah, blah, blah. Let's focus on the trivial bundle P. And even further, let's focus on the trivial electromagnetic bundle and see how we can actually descend to the quotient F mod G whenever that quotient exists. Well, not F mod G, but in our case, X mod G. G was an isometry of X. So you see, in this simplified setting, I have the minimally coupled metric term, and I have the minimally coupled global connection one form for the electromagnetic field. Okay. Then I write it out. I write out the minimal coupling and view it as a symmetric tensor here, and just the one form on what? On OI on S1 times X, which is evaluated on those extended differential of the extended embedding maps. The embedding map in S1X is identity on S1 and then X on S1. It maps me into S1 times X. And I'm taking the derivative. And I view those tensors obtained from minimal coupling as evaluating on these tangents. And what do I see? You see, they enter into the action function. But the gauge fields, the coupling gauge fields, the small a's, they enter algebraic, non-dynamic. So they enter as sort of Lagrange multipliers. So how about integrating out the field equations as they roll their regarding and descending on the surface of constraints? When can you do it? As it happens, you can do it when there is a metric on the fibers of the gauging bundle, which is inverted metric, right? Which means when the action is free. When the action is free, and not surprisingly, so free and proper action gives you access to F mod G, X mod G. If the action is free, you can integrate out the field equations, and what you see is the appearance of. So you just plot back the formulae that you get for small r a by solving the Lagrange equations for small a. You plug them back into these formulae. And what you get is new metric tensor and a new electromagnetic gauge field, which just happens to be G basic, which means that it descends to F the X mod G. In this sense, minimal coupling and whatever comes on top of it actually affects the descent, the reduction of the space of determined degrees of freedom from X to X mod G, whenever X mod G, of course, can be understood as a valid target for So a smooth manifold, a valid target for a charge point particle propagation. Okay, good. Now, which bundle to choose? This we have discussed. Yoneda. Okay, guys, lecture 2. We are done with point particles. Now it's time to get our hands on something serious, right? Like playing with the topology of the charge distribution. So we have understood exactly how complicated the description of dynamics of a point-like charge probe in an external electromagnetic field, a possibly non-trivial space-time topology, like Aharonov-Bohm type topology, may get. And then, if we want to gauge some symmetry in this dynamics, how complicated or how simple by now it may be, how intuitive, thanks to the introduction of defects, which implement gauge symmetry and tell us the structure, no matter how convoluted, we should take on the electromagnetic bundle. So now we shall go further, and now we shall play with the topology of charge distribution. So we shall now consider linear charge distributions, and for precisely the same reason as as I was previously choosing an Aharonov-Bohm contour, I will take the distribution to be closed. So I will consider charge loops propagating in space. These are our celebrated strings, which exist or otherwise, but still find some fits. So we'll be. By the way, you see, the reason I'm still slightly disinclined to be talking about strings, because maybe the mood is not right for talking about strings anymore. But you see, the field theories that describe critical string theories, such as the two-dimensional sigma model with conformal symmetry, appear everywhere. And for example, if, in more modern language, if you consider collective excitations of quantum spin chains, and you send the spin waves against one another, the effective field theory of slow spins is a particular two-dimensional conformal field theory known as the Berzomino-Novikov model of strings on groups. So strings on groups tell us how slow spinning is scattered. So it is still meaningful to consider charge loop. Okay. So yeah. So I want to keep the previous logic, namely that I have this current in a space-time in which there is in a space-time, so in a metric manifold, which is also permeated by, well, now not a two-form, because the potential of the two-form couples to a line, and now I have a charged loop which sweeps a two-dimensional surface. So the current is a two-dimensional surface, a cube, a current cube. And so what can couple to a current cube? A two-form. And the curvature of that two-form will be our Maxwell-type field, which will define a Lorentz-type deflection from geodesic motion. So geodesic motion for a loop is a minimal embedding of that surface in a given metric, and then deflections are described by Lorentz-type forces. Okay, so the current, as stated, is modeled on the volume for a two-dimensional submanifold in a metric manifold XG, with the compact intersection with any equitemporal slice in X. And again, for the sake of simplicity, and I will rely, I assume this to be the current geometry to be of the Aharonov-Bohm topology. So I consider two coordinate currents, which form a closed, compact, two-dimensional submanifold in X, which would be minimally embedded, but if not for the fact that the loop is charged, and so there are forces which deflect it from minimal embedding. So now, again, I have this part in the action functional which describes minimal embedding, geodesic motion of in xg, and then I have something which I now propose to attack somewhat differently. Rather than just soil our hands with this Ansatz 0, Ansatz 1, Ansatz 2 und nicht schießen. Bitte, instead of doing that, we will try to constrain this correction, this topological term in the Dirac-Feynman amplitude, to do the right job. There won't be too many constraints and we'll pin it down. So let's. So what should it be? So first of all, what previously was line holonomy and evaluated on 1 cycles in X, now will be a mapping from 2 cycles, those closed boundary-less surfaces in X, with values in U1. And now we have a simple principle that if you have 2 non-interacting cluster systems, then the action functional is additive. So if it's non-interacting, then the action functional for the system consisting of 2 non-interacting subsystems is the sum of the action functionals for the system. But now we have something which is supposed to like exponentiate the action functional. So this means that if I compute this thingy, chi cube, on a pair of non-intersecting, because that's the only interaction that we have in game here, in town, sorry, or in the village, or whatever. If I compute it on a pair of non-intersecting 2 cycles, it should be the product of the evaluations of chi q on each of them. That's point 1. So that's classical notion of non-interaction. Or rather additivity of actions or multiplicativity of Dirac-Feynman amplitudes for non-interacting subsystems. But then there's another thing. The next thing, and that's the last thing, promise, is that when I apply the principle of least action to this Dirac-Feynman amplitude, it should spit out geodesic motion, so minimal embedding, up to Lorentz type. And that's it. That's what I need the action functional for. And it happens to be a quantum mechanical object or pre-quantum mechanical object, but I need not know that or impose that. I already have by demanding that it maps to U1. It's well defined. Okay, so let's do the calculus. So you see, so how would I model how would I model a perturbation of a given embedding? I would model it by a vector field on X. So a perturbation of a given embedding is I flow it along a vector field, locally smooth vector field on X. I just flow it. And demand that at linear level, the flow doesn't change the action, the Dirac-Feynman number. So let us compute it using the constraints that we have introduced in the first place. Now do. Okay, so here's the thing. What I want is the stylus. Oh, sorry. Yeah, thank you. So I want this Lorentz force type contribution to the field equations. Here it is. That's what it is. And now I demand that this be. Okay, remember that the Dirac-Feynman amplitude is like an exponentiated action function. So I should differentiate the flow phi v is the flow of a vector field v, but by time t, from the initial condition, which is our surface, flowing the surface, embedded surface. I take the derivative in time, set time equal to 0, so that's the linear contribution. But since this is an exponentiated action, so I divide by the action at the initial condition. And now I compute. So I can pull this term under the derivative and use the fact that chi is a homomorphism. Chi of two cycles is chi on their sum. So I put it as a sum. Ta-da. But now the division is changing the orientation of the cycle. So if I divide by chi of something, this means I take chi of the inverse of the cycle, but the inverse of the 2 cycle is the cycle with inverted orientation. So I have the sum of. So now what's the geometry? I have my embedding, I flow it, I have the flow one, and I invert the orientation of this guy. What do I get? I get a boundary of the cylinder. get the boundary of the flow cylinder. So here I have the differential of the boundary of the cylinder, and this means that all I have to do, and this is a natural solution, I'm not saying that the unique one, but I couldn't think of any better one really, is that whenever I have a boundary of a three chain in X, and I evaluate on this two cycle, maybe the trivial one, the boundary, my chi, then it is given by what naturally gives me this thing. There should be a Q here in order to produce this. I mean, if you just take this and differentiate, you get the Lorentz force. But then we're done. This is Chigurh-Simon's differential character. Homomorphism from the abelian group category from the group free generated by two cycles into U1, that's condition 1. Independent multiplicativity of the Riemann amplitude for non-interacting systems, and Lorentz-type forces on a boundary of a three chain. It evaluates simply as that. So it's a Chigurh-Simon's differential character of curvature. And again, a mathematician comes with a good theorem which says differential characters, Chigurh-Simon differential characters, are in one-to-one correspondence with classes in a certain hypercohomology, which due to H, this three form, or F here, sorry, which due to the three form F, what we previously did to the two form F, the Maxwell field, by choosing a good open cover on X and trivializing it locally. F on Y is dAI, and Aj minus AI is again exactly so. So let's inspect the Davidson-Deligne hypercohomology, which we will then geometrize. Because we see the differential character. I will give you the differential characters in terms of the suitable Davidson-Deligne two-cos cycle, but first let me tell you what the cohomology is. So we start with a complex of sheaves. Sheaves are no terrible beasts. I mean, what we're talking about is locally smooth one, locally smooth two forms, locally smooth one forms, locally smooth U1 value. They can, if I have a local guy here, a local guy here, they overlap on the and they are the same on the overlap of their respective domains. I can glue a big one. Big deal. That's cheap, right? And I can add sections. Like I can multiply maps. They take values in U1, so this is abelian multiplication, so it's addition. And I can add locally smooth forms. That's all I mean by sheaf here. So we have a complex of sheaves. So we have the locally smooth U1 valued maps, which by the logarithmic derivative map into locally smooth one forms on X, which by the standard derivative map into locally smooth two forms, and so on until we hit the dimension of our membrane loop world sheet or whatever. Previously P was 0 and we were just having the surface. Now P is 1 and we have some two-dimensional surface compact with our boundary embedded in it. Like we could do it for a membrane or whatever. So we have this Deligne complex, and now here's the bicomplex. So we consider the following object. Remember, maybe I should motivate. So previously we were trivializing the Maxwell field F. F over OI was an AI. So it was the one form with the one index of the cover. But AJ minus AI was ID log GIJ. Here was GIJ, two indices of the cover, and mapping into U1. So we somehow want to lay our hands on objects which carry several indices of the cover and take values in one of those sheets. And we have this total degree. Two indices, Gij, just a map, a 0 for. 2 plus 0 is 2, the last time I checked. And then could be 20, but yeah. Anyway, so, and then there is AI, a one form with one index. 1 plus 1, the same result. So we can see that there is some kind of total degree which adds the number of indices degree and the form degree. And this is what we're doing. Look, we have one, well, it's a check complex. So in Polish we have to say Czech movie when you don't understand a thing, although you should because it's a brotherly language. So here's the Czech movie. So it's a Czech cohomology, hence it carries a 0 and there's the 1 index. Right. How else? So anyway, so there are guys which have 1 index and there are functions 0, 0. 0 plus 0 is 0. Then there are guys which have 1 index of the cover. No, 1, 0, sorry. 1, 0. No, it's 0, 0. No, we're counting the number of indices minus 1. This is 1. My number of indices minus 1. So we have 1 index and a 1 form. That's 0 plus 1 minus 1 plus 0, which is 1. And we have 2 indices and a function. So that's 2 minus 1 plus 0, which is 1. So this here has total degree, the same total degree. And likewise here, we have 1 index piece with form degree 2, 2 indices piece with form degree 1, and 3 index piece with form degree 0. And they form the diagonal subcomplex of this cohomological bicomplex, in which vertically we move with the differentials, the logarithmic differential from UN valued maps to one forms, and the standard Durand differential from forms to forms of higher degree. And horizontally, we move with Czech boundary operators. You have seen them. You see, when I wrote AJ minus AI, in fancy terms, this is the boundary of A. When I pass from OI to OIJ, then I have IAJ, so weighted sums of sections. I need to be able to add sections, to write weighted sums thereof, and then restrict. I should be able to restrict them because I'm taking AJ minus AI where both exist on OIJ. Restriction, addition, pressure. Right? So here I have my Czech boundary operators, and as it happens, if you just look at how they're defined, then Czech boundaries and Durand boundaries, the logarithmic one and others, they commute, which means that I have a bicomplex. I have the diagonal Deligne operator, which is some weighted sum of the two boundaries, and I can move in this diagonal subcomplex. And I can compute its cohomology. And this is the Bayesian-Deligne cohomology. It's the diagonal, it's the total cohomology of the diagonal subcomplex in the Czech Deligne complex associated with a given Deligne complex of sheaves. And here's an example of an action of the Deligne operator on a 2 cochain, which now consists of, let's count it, check-wise. So there's a 2 form with one index. 1 minus 1 is 0, so 2 plus 0 is 2. Then there is a 1 form with 2 indices on OIJs. And then there is a U1 valued map with 3 indices on OIJKs. Let's see what happens if I knock it with a Deligne. I get BAIJ minus BJ minus BI restricted to IJ, and so on and so forth. And if I see that if I set it equal to 0, 1, I get there are BJs whose exterior derivative glues. Because you see, if this is 0 and I apply D to it, it means that DBJ is equal to DBI on OIJ. It's sheaf, it glues. Right? If it's the same on OIJ, it gives me something global, something which restricts as DBJ or DBI, but it's global. That's the 3 form, which we have trivialized over OI, is DBI. But then BJ minus BI, previously the gluing of AJ and AI was given by the transition mappings of the principal bundle. Now it's given by 1 forms, AIJs. And then 1 forms glue in some way, in a way that is controlled by U1 valued maps with 3 indices, because the gluing is on OI intersected with OJ intersected with OK. OK is this. So here we have the Bayesian-Deligne hypercohomology, and now we have gerbs. Gerbs in cohomological terms. And the gerbs will give us differential characters, which we'll interpret as those topological terms in the Rafal. in Aharonov situation. Okay, so we have gerbs, which are just classes in the top Beilinson-Deligne cohomology. So basically here, this would be the class. It starts in the upper left corner and extends like so. I take D, which takes me here, and here, and here. And I produce this equation. And I demand this to be 0. And these are the data of the gerb. How so? F restricted to OI is a BI. The BI is moved by the AJs because we're taking a good open cover, mind you. So this would be a cohomology of the manifold and not the one for a given open cover. The open cover had better be good for us to be able to apply the Poincaré. So we have gerbs as classes in this Beilinson-Deligne cohomology group. Now, to any such class, I can associate, as stated before, a curvature which is global. And these are, well, let's take p equal to 1. These are closed three forms on X. And since we have the co-cycle condition for Gijk's, I remind you, the integrality ofCijk's for bundles meant that the Maxwell form was supposed to be integral. Likewise here, we'll maybe do it in the tutorial. You see that ifCijk's are integral, then the Maxwell form necessarily is an integral to form. So likewise here, it's not any closed p plus 2 forms that we get by taking d of the top component. No, it's the integral ones. And what is in the kernel of the curvature assignment? Well, those guys which have curvature 0, so flat gerbs. And you can easily convince yourself on this one, we can also do in the tutorial, that flat gerbs can actually be captured by the lower component in this Beilinson-Deligne co-cycle. So local constants with as many indices as should be, so the gerb is 4 indices. Classes of the gerbs. And now we have a whole hierarchy of morphisms. Hence the 2 categories of gerbs, 3 categories of 2 gerbs, and so on and so forth. And hence our ability to describe defects in the sigma models. So we have a co-cycle, which is a gerb, but its data are only well defined up to something in the kernel of the Deligne operator. So if we now take something, correct the data by something Deligne exact, we get an equivalent structure. Just as when we trivialize F, we get AI, Gij, and we could correct it by a principal bundle automorphism in geometric terms, or Deligne of HI, which was a gauge transformation. Well, here, the gauge transformation will be described for the gerb by actually a one form and a UN valued map. But then if I choose a particular one automorphism, I can still correct it by something in the kernel of the Deligne corresponding Deligne operator. And if I correct it by something Deligne exact, I get an equivalent morphism of the first type, and so there will be a morphism of the secondary type, which relates morphism of the primary type. And I can go on like that. I have morphisms between morphisms between morphisms, and so on and so forth, until I hit the floor. For gerbs, for 3 forms, I have a 2 co-cycle, and then I have 1 isomorphisms, which already you can see carry the data of something like a bundle. And then I have morphism between these, because it makes no sense to take the 2 bundles, but morphisms. And so you have 2 isomorphisms between gerb ones. Okay. This whole hypercohomological structure gives rise to a certain weak, but never mind, let's say 2 category for gerbs, where I have precisely objects factored in by gerbs, so those 2 co-cycles in hypercohomology. Isomorphisms between them, so Deligne equivalences between them are morphisms of the first type, And on the Hom set of morphisms, we have the structure of the category, so there are further morphisms. That's for the two categories. But that's not all about two categories, but still. There are distinguished trivial gerbs. Previously, we had distinguished trivial bundles, which were just one form on the base. Well, here, trivial gerbs are very similar. There are two forms on the base, whose exterior derivatives are the curvatures. So if the curvature trivializes globally, I speak of a trivial gerb. If the Maxwell cube trivializes globally, I speak of a trivial bundle. Good. And then we have a bunch of structures which I will be using liberally in what follows, hence I'm just flashing them at you. We have the Deligne product. So if you think of two classes in this hypercohomology, you may define their product as, not that since you're dealing with sheaves, you may define their product assuming the same trivializing cover for both. So you really take classes associated with the same good open cover of X. You take their product to be, you take representatives and add them component-wise. So you add the two forms, you add the one forms, and you multiply the U1 value. And this is a binary operation on in the hypercohomology, which is later geometrized. You can pull them back in a consistent way. So never mind, you can pull them back. The thing is that you have to coordinate the two open covers. If you have an open cover on a manifold into which you map, you should take an open cover on your manifold, which is the pullback of that. And then have a map on indices by which you may pull back appropriate objects from the codomain of your map, smooth map. And now you also have the holonomy. So the differential characters which we saw emerge from our purely physical considerations concerning what the correction to the metric term should be in order to do the job for us, or to describe the Lorentz-like deflection from geodesic event. And so the holonomy actually requires the following. In order to write it out, and I will write it out in terms of the hypercohomology data of the gerb, because that's what gerbs are to us at the moment. They will geometrize in the environment. You have to so you take your two-dimensional boundary-less compact surface which you embed in X. You take it there on X. There is an open cover, good open cover. In the worst case, a good open cover on which the gerb trivializes. So you have the bunch of BIs, AIJs, GIJs. Good. You want to pull it back. So what you do is for a given embedding map X, you tesselize, I suppose that's the word. You triangulate, except that it'll be a honeycomb triangulation, so not exactly triangles. So you tessellate your surface. Say you triangulate it, because triangulations always exist. So you triangulate it in such a way that this embedding map X maps every triangle into some open set. Why is that? Because by this embedding map, you want to pull back from that open set the corresponding BI. Okay? I'm playing on the logic, on the Ansatz 0, Ansatz 1 logic of the reconstruction of the line holonomy in the previous example. So if I have a mapping of triangles into opens, then necessarily I also have a mapping of edges into opens and vertices of this triangulation into opens. So that's done. And now, I have a triangulation. In order to make things simple, I want to exchange this triangulation for a honeycomb tessellation, and that's easy. Since every multivalent, so 4 plus valent vertex of the triangulation sits in an open, I can resolve it and make sure that all vertices of the resulting tessellation are trivalent. And if I have trivalent vertices, it's a simple formula, which I give you here. So I'm pulling back to each face of the honeycomb tessellation, the corresponding two form. Then for each face, I have its edges So to each edge, I pull back the corresponding one form with suitable indices. One edge index, one one plaquette index, and then to each vertex of each edge of each plaquette, I pull back the suitable one. It's a closed formula. It's nasty, but it's closed. And you might say, well, okay, so now we have reached our goal because we have been kind, gentle, and rigorous, and we have our holonomy. So what? So much more, because as it happens, as was observed by Gawęcki back in 1987, if you now give me a co-cycle in Bayes-Sundelin cohomology, two co-cycles, describing a jerk, then I will use its cohomological data to construct a line bundle over the configuration space of my theory. So what is the configuration? What are the configurations in this two-dimensional field theory? There are loops in X. This is a configuration. A state is a loop with a kinetic momentum. But a configuration is a loop. That's an equitemporal slice, a loop. So now I will construct a line bundle over the loop space using the hypercohomological data of the jerk. To any jerk, there will be this bundle. And I will not prove it, I will not show it because that would take quite some time, but the bundle will come with connection, and the curvature of the connection will be the presymplectic form of the two-dimensional field theory, which you can derive from its Lagrangian formulation, a la Tuchyjev, Gawęcki, Kijowski, and the Szczytba brothers. So to any Lagrangian field theory, you have a presymplectic form. And if you have a line bundle over the space, say, of the configuration space, let's say, of your Lagrangian field theory, and this line bundle comes with a connection whose curvature is the presymplectic form of your field theory, then you have pre-quantization. First step towards geometric quantization. This, now, a much more precise sense, jerk is a quantum mechanical object which selects the quantization mode for your two-dimensional. I didn't tell you that before, but this bundle, which we have, the Maxwell bundle, its sections can also be viewed upon suitable polarization, so the choice of representation, position, momentum, you name it, they can be viewed as wave functionals or wave functions of this point-like charge. Here, the sections of this transgression bundle can be viewed as wave functionals of the two dimensions of the loop. Okay, good. So now I will construct the bundle only as a topological object because I don't want to deal with the theology or the differential geometry of the infinite dimensional loop space. But here it is. So we have to topologize this loop space somehow, and the way to do so, it's S1 maps of S1 into X. S is compact. S1 is compact. X comes with a metric. So we have a compact open topology on the mapping space S1 into X, whose basis consists of those loops, which for a given compact in S1 and for a given open in X, put the compact in the open. That's the basis of this compact open. And then I can form an open cover consistent with this choice of topology, so the index of the cover is two things. It's a triangulation of my loop, segmentation of my circle, and a choice of an open cover on X. And how so? Well, I have a segmentation of the circle. I have a segment, so I have its decomposition into edges, which meet at vertices. And now I call an open set, the set of all those loops, such that the edge X, the edge E, is mapped by this loop into a given OI of E, I being this other label of the open cover, namely the choice of an open cover on X, and similarly for the vertex. As you run through all segmentations of the circle and all open covers with the corresponding index set on X, you cover the entire loop space. and consistency with the choice of the topology that I described. There is a way, maybe let us not discuss it in detail because it's pretty technical. There is a way to discuss intersections of such opens. Basically, you intersect segmentations and you keep the two open covers in the target, and then out of the data of the germ, out of the hypercohomological data of the germ, you can construct, written here, for any loop in the intersection of two opens as described, you can associate a mapping of that loop into U1, a transition function. Because as it happens, if you look at the gluings of the hypercohomological data of the germ, they imply the co-cycle condition for this co-cycle with values in U1, which by the clutching construction for bundles defines for me a bundle over the loop space. So now the bundle is, I take O, the local model, O, J. J is this index of the covering, which is two things, segmentation of the circle and an open cover of X, times, well, let's do the pre-quantum bundle, so times C, and I glue the local models by the equivalence relation defined by the co-cycle determined by the hypercohomological data of the germ, and that's the pre-quantum. Well, that's a bundle at the moment, but I'm telling you that it's a pre-quantum bundle. And finally, or nicely enough, if I now have an isomorphism between two sets of cohomological data, so they differ by something nearly exact, I can take the data of the automorph of the one isomorphism and similarly transgress them to data of an automorphism of the pre-quantum bundle. So really the germ is like giving me the pre-quantum bundle and its automorphisms transgress to automorphisms of the pre-quantum bundle. So these are pre-quantizable symmetries of my theory. And this is the point, to stress, definitely, that you see, demanding that ordinary symmetries that you encounter in the world of Lagrangian field theories with tensorial coupling now linked to automorphisms of this higher geometric structure, the germ, because they transgress to automorphisms of the corresponding pre-quantum bundles, is a serious condition, and it super selects only some of the automorphisms of the action function. Those that actually live to the higher geometry. It's a condition, and it's like a quantum mechanical consistency condition on classical. Previously we saw it. Before we lifted the gauge symmetry to an equivariant structure, which is an automorphism, roughly speaking, of the jerk, of the nerve of the action groupoid, we only had classical symmetries which needn't be quantum mechanically consistent. There may be obstructions in the form of those flat bundles delta. So there may be anomalies. So lifting the symmetries actually ensures that, well, we have the first quantum mechanical meaningfulness check, sanity check. And then you also, in those hypercohomological terms, you can now classifying your models. And it has got us pretty far in this controlled setting of charge and loop mechanics with a compact Lie group as a target space. These are so Witten-Gawęcki models, where the literature is extensive, the conformal field theory model techniques are numerous and very, very robust. And they have produced a huge classification scheme for those conformal field theories. And together with Gawęcki and Waldow, and also Nuno Reis, Gawęcki's former students, we have been able to recover all the classification results obtained by hardcore conformal field theory techniques by using at the right classical object. That's the point I'm making here. One of the possible answers to the question, how should I quantize the theory, is not at all. Just find the right classical structure, which is pre-quantum mechanical, for example. This one is the germ. And look at the cohomology that classifies inequivalence, which will tell you what are the inequivalent two-dimensional models of two-dimensional charge field mechanics. Look at its automorphisms, inequivalent, and in this way classify pre-quantizable symmetries of this mechanics, and so on and so forth. You get cohomological means of classifying field theories, defined in terms of in the presence of charges, characters, and this is what I wanted to advocate here, and I suppose that on this note